Good morning, my dear students. Today I am taking your first class of physics. As you had told me yesterday in the Google Meet that most of you have not purchased your books till now. So today I am giving you the PDF of lesson number 2, that is unit and measurement. So this video is created in such a way that you can go through the PDF, you will get the chapter, and you can listen to my voice and understand the lesson. Since there are no derivations and most of the portion is you have studied in class 9, that is the repetition. So we will do this chapter. Okay. So let's start with lesson number 1. Lesson number 2, unit and measurement. Lesson 2, unit and measurement and error analysis. So the chapter is unit and measurement and error analysis. Since the board has reduced the syllabus, so the much of the syllabus has been reduced. Error analysis is no more in your syllabus. Okay. So I have already given you the new PDF of the reduced syllabus that is given in your group. Please follow that. Okay. So the first thing we are talking in the chapter unit and measurement. What is the need for measurement? This is a basic definition of physics. What do we do in physics, or what do we study in physics? Physics itself is a science of measurement. Okay. Physics, what do we study? We study measurements in science or in physics. For example, height, weight, height, weight, time, length, mass, all these quantities are measured in physics. Lord Kelvin once said, when you can measure what you are speaking about and express it in numbers, you know something about it. But when you cannot express it in numbers, your knowledge is of meager and unsatisfactory kind. What does his statement mean? Anything that is theoretical, anything is that is not having any mathematical calculations or mathematical expressions, then that knowledge is meager and unsatisfactory. Then we come to the next topic, physical quantities. So what are physical quantity? Quantity that is linked to physical phenomena and which is subjected to measurement and may be treated as a physical quantity. Examples: length, mass, time, force, speed, etc. These are all physical quantities. They are all linked to a physical phenomena. On the other hand, we in our daily life come across some quantities which are non-measurable, which are abstract, that are taught in abstract noun, feelings, emotions, squeezing, love, hate. These are not put under physical quantities. So any quantity that can be measured is a physical quantity. Quantities that cannot be measured are abstract. Now, units of measurement. So in order to measure a physical quantity, we assume a certain magnitude of this quantity as a standard and call it unit of that quantity. If you could, those students whom I have taught in 9th class, you must have remembered that I had given an example. The different students are asked to measure the length of the table. So they measure the distance by their palm. And each student is getting a different answer. Why? Because the size of the palm of each student is different. isn't it? Then you are asked to measure by elbow. Again, you are getting different answers. So we need a standard quantity so that everybody gets the same answer. So what do? We use a scale. We are using a scale. And if you measure, if you use a meter scale, you will find that the answers are accurate. Almost everybody is getting the same answer. So that is why we need a standard quantity which we call a unit of that quantity. Okay, like a given length of an iron rod is considered as 1 meter, or a given mass, any mass that was initially taken was told to be 1 kilogram. Now whatever we are measuring in terms of that mass, we are getting its magnitude. Suppose the length is 5 times the length of the meter, then 5 is magnitude and meter becomes the unit. Similarly, if the weight is or mass is 10 times the mass of kilogram, it becomes 10 kg, where 10 is the magnitude of the quantity and kg is the unit. So any physical quantity, when you talk about any physical quantity, it has got two things. One, the unit, second, the numerical value. The numerical value is known as the magnitude of that quantity, like 20 meters. 20 is magnitude and meters is unit. What kind of unit? What is unit? Unit is the unit in which the quantity is measured. What kind of unit should be there? It should be of suitable size, precisely defined. What do you mean by precisely defined? Its value should not change. Change with circumstances, weather, conditions. Okay? Easily accessible and reproducible. That is very important. Neither the unit be very small nor the unit be very large. It should be of appropriate size so that we can get its smaller values also and bigger unit also. Okay, and its value should not change with time, place and physical conditions. So now we come to a very important point. When we are expressing any physical quantity, it has got two parts. N1 is the magnitude and U1 is the unit. N1, U1, 20 meters. So 20 is N1 magnitude and meter is unit. Now, as I told you, units are reproducible. So if we change unit 1 from meters to centimeters, then it becomes 20 into 100, that is 2000 centimeter. Okay, so N1 U1 equal to N2 U2. The next important topic is fundamental quantities and fundamental units. So first of all, fundamental quantities and fundamental units. The fundamental quantities are independent of one another and no one can neither be derived from the other nor can be further resolved into more simpler units. That is, in simple words, fundamental units or fundamental quantities are independent of each other. They have no relation with each other. Like we have got three fundamental quantities: length, mass and time. Length and mass and time, they are independent of each other. You cannot derive length from mass or mass from time. These quantities are known as fundamental quantities and their units are known as fundamental units. Okay, so there are three basic fundamental quantities: length, mass, and time, and their units are meter, kilogram, second. In the same way, there are physical quantities occurring in electromagnetism, thermodynamics, and optics: electric current, thermodynamic nature, temperature, amount of substance, and luminous intensities. They are also considered as physical fundamental quantities, and their units are fundamental units. All these you have also studied in class 9. The unit of our fundamental quantities, like for example, length, mass, time, electric current, thermodynamic temperature, amount of substance, and luminous intensity, are called derived units. Okay, all the units other than these fundamental quantities, these are derived units. So all those units that are not dependent upon fundamental quantities or that are taken out from fundamental quantities are known as derived quantities, and the units are known as derived units. Like for example, speed. Speed is distance upon time. So distance is length, time is second. So it is meter per second. So that is a derived unit. Or force, mass into acceleration, kilogram meter per second square. That is derived unit. Now, since we have talked about units and we have already discussed units, systems of units, there are different systems of units that have been followed all over the globe. The simplest one, easiest one CGS system. It is also known as Gaussian system and is based on centimeter, C for centimeter, G for gram, and S for second. So these are the basic fundamental length, mass, and time. Length is measured in centimeter, weight or mass is measured in grams, and time is measured in second, respectively. It is a metric system or decimal system because multiples and some multiples of fundamental units are obtained in the powers of 10. Then the British system, that is known as foot-pound system. Length in foot, mass in pound, time in second. Okay, so in WWE championship, the wrestler's weight is still measured in pound, and if you go to the market to buy dumbbell, you will find the mass is still in pound. Okay, boxing bouts, the weight of the wrestlers are still in pounds. So since we have been ruled by Britishers from long time, we used to follow FPS system in India before independence. Nowadays we have switched over to metric system. Then the third system is MKS system. Again, length, mass, and time have been taken as the quantities, fundamental quantities. So M represents meter, K represents kilogram, S represents second. Now there are so many systems. Same value of any physical quantity is represented in different systems followed in different part of the world, creates a problem. So there was a system of international unit, SI unit, which is followed in physics, and that is considered to be the best system overall followed all over the globe. So basically it is MKS system only. All fundamental quantities have got SI units. Okay, let's discuss them. First one, length. Length SI unit meter. Small m is the symbol. Mass kilogram. Time second. current or electric current ampere represented by a capital A, thermodynamic temperature Kelvin K, amount of substance mole, luminous intensity candela. Then there are certain supplementary angles: plane angle, radian, solid angle, steradian. Like CGS and SI system, CGS and MK system, the SI unit is also a metric system. The SI system is having certain advantage over other system. It is a rationalist system, that is only one unit for one physical quantity. Like for example, you must have studied about different kind of energies: kinetic energy, potential energy, solar energy, mechanical energy, heat energy, light energy. All have got only one unit, joule. Okay. In MK system, these energies are expressed in joules. If it is heat, it is expressed in kilocalories. Electrical energy, it is measured in watt hour or kilowatt hour. Then it is a coherent system. That is, all derived units can be obtained simply by multiplying or dividing the fundamental units without introducing any numerical factor. The third point, in electricity, the SI system or SI units are the same as the practical units. That is, the SI unit for current, potential, resistance, inductance, etc. are respectively ampere, volt, ohm, Henry, etc. Definition of fundamental SI units. The 7 fundamental units are defined as under the definitions given. 1 meter. 1 meter is defined as the distance containing 1650763.73 wavelengths of the orange red light emitted by pure krypton 86. Other units: 1 kilometer, 10 raised to power 3 meter, 1 centimeter, 10 raised to power 2 meter, 1 millimeter, 10 raised to power 3 meter, 1 micron, 10 raised to power 6 meter, 1 nanometer, 10 raised to power 9 meter, 1 angstrom, 10 raised to power 10 meter, 1 Fermi, 10 raised to power 15 meter. All of them are very important. All these units, right from centimeter, millimeter, micron, nanometer, angstrom and Fermi, they are very important because most of the physical quantities in electricity and nuclear physics are measured in such small lengths. So you should know what is a micron, what is nanometer, what is angstrom, what is Fermi. Okay. So pay attention on these smaller units. Then for measuring very small areas, we use unit barn, BARN, that is equal to 10 raised to power minus 28 meter square. Then we have to measure very large distances, like the distance of the sun from the earth. Then we are using astronomical unit. One astronomical unit is the average distance of the sun from the earth and has the numerical value given by 1.496 10 raised to power 11 meter, approximately 1.5 into 10 raised to power 11 meter. Then light year, the distance travelled by the light in 1 year. So 1 light year is equal to 9.46 into 10 raised to power 15 meter, approximately of the order 10 raised to power 16 meter. Then 1 parsec. 1 parsec is the distance at which average radius of the Earth's orbit around Sun would subtend an angle of 1 second. So 1 parsec is equal to 1 astronomical unit upon 1 second. So there is a bit of calculation in there for you. 1 parsec is equal to 3.26 light year. Then we come to the second unit, kilogram. So 1 kilogram is defined as the mass of the platinum iridium cylinder kept in Paris. This is what was told to you in 9th class also. In practice, 1 liter of water is equal to 1 kilogram. If you could remember this, 1 liter of water is only equal to 1 kilogram at 4 degrees Celsius. But 1 liter of refined oil is not equal to 1 kilogram. 1 liter of refined oil is equal to only 897 grams. So it is only for water where we can consider that 1 liter equal to 1 kilogram. Why? Because the density of water is 1 gram per centimeter cube. And we know we have the formula density is equal to mass upon volume. If density is 1, then mass equal to volume. So in case of water, density of water is 1 gram per centimeter cube. Therefore 1 gram of water is equal to 1 cc. 1 liter equal to 1000 grams or equal to 1 kilogram. Higher or multiple units of kilogram. 10 is to power 3 kg, 1 metric ton, 1 quintal, 100 kilograms, 1 gram, 10 is to minus 3 kilogram, 1 milligram, 10 is to power minus 6 kilogram or 10 is to power minus 3 gram. Okay, to measure the mass of to measure the mass of atom, we have unified atomic mass unit, that is defined as 1/12 of mass of carbon-12 isotope. So 1 unified atomic mass unit equal to 1.66 into 10 raised to power minus 27 kilograms. Then third fundamental unit is second. 1 second is defined as the time interval in which cesium-133 atom completes 91926317770 vibrations in an atomic clock. Rather than other are prefixes. Millisecond means 10 raised to minus 3 seconds. Micro means 10 raised to minus 6 seconds. Nanosecond means 10 raised to power minus 9 seconds. Picoseconds 10 raised to minus 12 seconds. Then there is a shake. You know what is shake? 10 raised to power minus 8 seconds. Another unit for electric current is ampere. 1 ampere. Ampere is the SI unit for current. You had studied the formula of current in 10th class. I is equal to Q upon T, and coulomb per second. But it's not defined by this formula. Rather, it is defined on magnetism. 1 ampere is defined as the current which, when maintained in two parallel and straight conductors of infinite length and negligible cross sections placed in vacuum at a distance of 1 meter apart, would produce a force of 2 into 10 raised to power minus 7 Newton per meter length between the conductor. In simple word, if there are two wires of infinite length placed at a distance of 1 meter apart and experiences a force of 2 into 10 raised to power minus 7 Newton per meter, then the current flowing in the wire is equal to 1 ampere. SI unit for temperature is Kelvin. 1 Kelvin is 1 upon 273.16 part of thermodynamic temperature of the triple point of water. Mole. Mole is the unit of amount of substance. Mole is defined as the amount of substance of a system which contains elementary entities as there are in 0.012 kg of carbon-12, or we can say that has got particles equal to Avogadro's number. The next one is luminous intensity SI unit, that is candela. Luminous intensity, you must have seen nowadays we are using LED bulbs. Now LED bulb, earlier we used to have 100 watt electric bulb, then we had 15 watt CFL. Now the same intensity of light produced by 15 watt of CFL is given by 5 watt of LED. So light, luminous intensity is the light in which we can see white color light that is emitted out by the bulb. That is luminous intensity. So 1 candela is the luminous intensity in the perpendicular direction or surface of 1 upon 6 lakh 1 upon 6 lakh meter square of a black body at the temperature of freezing platinum under a pressure of 101.325 Newton per meter square. Then there are supplementary units. Radian. 1 radian is equal to 57.3 degree. Then we have steradian, that is equal to 1 steradian is the solid angle subtended at the center of a sphere by that area of the surface of the sphere which is equal to the square of the radius of the sphere. Now my dear students, these are all definitions. You are never asked to define them. You don't have to learn them by heart, but you should know them. What is important here? You should know the fundamental quantities and you should know their fundamental units. Okay? You should know their multiples and sub-multiple units. Okay? So rest of the lesson will continue in the next video. Thank you.